And hello, welcome. Okay, so today we're going to talk about the findpeaks. Okay, so what are we trying to do? I think the last video actually showed you how you use this findpeaks, and it should be inside this signal processing and communication module. Yeah, it should be inside the signal processing and communication module. Okay, you will find the instructions over here. Okay, how to find local maxima. This is a signal processing toolbox. Okay, signal processing toolbox. Okay, yeah, signal processing toolbox 8.6 for this version. So the function, if you install that, is called findpeaks. Okay, what do you need to do? Okay, it's basically to have your y inputs. Okay, so findpeaks is quite simple. If you have, let's say, your Fourier spectrum like this, okay, you have y of omega versus omega, or y of f versus f. Okay, your y of f will be in a particular vector, and your frequency, all the frequencies that you're plotting against, will be in another vector. What you're supposed to do to supply this findpeaks, okay, you're supposed to give it the y values first, followed by the x value. So for example, I will give the input first and then f, and that's how you do it. Okay, then there's the error displayed here. You expect peak finders expect a y to be real. So remember, your Fourier transform is definitely a complex number, so you have to do the absolute value first if you want to use this value. Take the absolute value of your Fourier transform in order to do this. Now we can see that okay, peak finder does its job. It has found our peak at 2 times 10 to the minus 3 hertz. You can see the peak here is automatically detected. However, it has also detected lots of other peaks here. As you can see, all the arrows over here, which obviously we don't want, because that's not our original peak. Okay, so in a sense, this peak finder thing is oversensitive. How do we adjust the sensitivity? Now there are a few ways you can do it. I'm going to run through them very briefly, and I'll tell you the one I'm using. Okay, one is with this thing called peak prominence. Okay, peak prominences. So this one, yeah, this one is basically the syntax of how you do this peak prominence thing. You do findpeaks, your y signal, your y vector, then your horizontal vector, your x vector, and you have to specify mean peak prominence, and then you just put some number there. Okay, so I'm going to do something like that. I'm going to enter in the same command, and I'm going to put mean peak prominence. Okay, I use a tab to complete, and I'll put 1. And let's see the graph now. All of a sudden, now I just entered the arbitrary number of 1, and basically, there's no more issue. It only finds the peak that we want, because this peak is so high compared to all the other so-called peaks here. So the arrows here aren't even showing up. Okay, and this is the simplest way to do it. And why is this thing so good? Peak prominence. Okay, if you notice, some Fourier transforms signals, the baseline actually shifts over time. So if we were to do, instead of the input, we give it the output, right? If we were to give it the output, yeah, we will see. You see, if you see this part, okay, your baseline actually shifts over time. Okay, let me zoom in again. You see, your baseline actually is dropping over time. All right. So if you actually look here, oh, this is not good. Yeah, if you actually look at this peak graph, okay, you see that it's sort of sloping downwards over the course of this whole thing, right? It's sloping downwards. Okay, and then there will be several peaks that you are seeing here. Okay, obviously these are like peaks, but they are likely to be noise. Okay, but they're higher than background noise, so to speak. So at the bottom here is all the background noise part, and you kind of want to make sure that your peak height is higher. I mean, your find peaks. You kind of define peaks to be, you know, any point that is significantly higher than the background noise. So for example, this one over here, it has a height of maybe 0.07, right? Over here. This will be considered a peak. But if this peak was over here in this very low frequency range, at the height of 0.07, you know, you will not be able to distinguish this peak from the background noise. Okay, because the background noise is so much, a peak of a height 0.07 will not be, you will not be able to distinguish it from background noise. So if you were to use, you know, maybe I would say the minimum peak height to be 0.07, okay, and the peak height is the length of the peak from height 0, then you're going to have a problem, because all the noise over here is going to be identified as peaks. So let me demonstrate to you. Okay, mean peak. If instead of prominence you use height, okay, mean peak height, and you put 0.07, you'll see that a lot of places are going to be designated as peaks as well. So this thing is again oversensitive. It will have identify all the other peaks also, but the problem is, you know, it's also detecting all of this stuff here, all of this noise as so-called peaks, which I think for our intents and purposes, we do not want to consider all of these peaks. So if you want to just say, okay, I need my peak height to be 0.07 more than the background, okay, then instead of peak height, you will use peak prominence. Okay, so peak prominence. So if your mean peak prominence, okay, if your mean peak prominence is 0.07, you'll notice that all the peaks on the left, they are no longer considered peaks. These are all background noise, and all of this here will be considered peaks. This one's a little bit more than background noise, but I mean, you can change the sensitivity. You can put the prominence threshold at 0.05. Now, of course, you would see that okay, maybe more of these smaller peaks are being detected. Okay, the rest are just considered background noise. So I mean, there are a few ways you can do this adjust the sensitivity, so to speak. You can use peak height. You can use peak prominence. Okay. Yeah. So this is what I like to do. Now, of course, if you take a look at the maximum peak height here, it is about 15 or 16 over here. All right, and the rest of them are just considered, you know, they are really not as tall. They are around, you know, 1, 0.2, all of that. You know, so how? Okay, the question is this. Now that we have more or less settled on using peak prominence, because this is kind of a more practical way of doing things. How are we going to do so? You know, how are we going to how are we going to decide what's the number we put here as our threshold? Okay, one quite easy way, the easiest way, I think. All right, because depending on your Fourier transform, you're going to have different peak heights, right? Okay, so you take the tallest peak height as your reference point. You take your tallest peak height as your reference point. Maybe you take your tallest peak height and you like divide it by 3. Okay, you divide it by 3 so that okay, so for this example, if your peak height is 15 and you divide by 3, okay, then your minimum peak prominence will be 5, right? 5 units, depending on what your unit is. And over here, all these peaks will not be registered. So what I'll do is I'll do absolute output divide by 3. Okay, absolute of the maximum of the output. So it will take the maximum of all of this, and you kind of just divide by 3. And see, now all the peaks here are not detected, so it's not very sensitive. You can actually have it to be a divide by 20 as well, so so that you can see, you know, all the stuff here. Now all of this is being detected, the rest of the peaks are not being detected at all. So it's really up to you to decide how sensitive you want these to be. Okay, and of course, if you want, yeah, you can even do this whole thing in log scale. Okay, because if you want to do it in decibels, you will be able to see more of the whole peak range. Okay, so yeah, so this is how you do it. Okay, log 10 divide by 3. Okay, so this is all now in log scale, and you will be able to see, you know, that this peak here is obviously the biggest peak. That was like 15 units tall, but now you're able to see all the adjacent peaks as well. Yeah, and now you also see number 3. You'll see that the baseline actually starts dropping over time. That's why it's very important to use this peak prominence rather than peak height. And if you divide it by 3, of course you will see that this sensitivity is so high, and it will just like register all these extra peaks here, which is not exactly what we want, but that's what we are getting. Okay, so anyway, this is what you'll get if you use the decibel mode, if you try to do the logarithmic. Okay, logarithmic mode, to try and you try and find peaks across the various order of magnitude, so to speak. Okay, but doing it this way, you're going to yeah, pretty much ensure that you'll be finding a lot more peaks than you might even want. Okay, alright, so that's basically what my code here is doing. Now let me explain the code over here. So basically I have a frequency data matrix or array. Here's frequency, here's the input frequency, this is the output. Okay, what I do is that I convert it into decibels first. You can use 10 times log 10 or 20 times log 10 depending on your signal. Usually for power signals, power signals you use 20 times log 10. For amplitude signals like voltage and current, you use 10. Okay, so it's really up to you, but anything to do with power or energy, the convention is to use 20 times log 10 to convert this input array into a decibel. Okay, so yeah, so I just put 10 here. Doesn't really matter because the whole idea of this peak finder is just to help us to identify peaks and, you know, point out where they are. So the threshold of the input, I would say I'll take the absolute value of the input, and then I'll find the maximum value. I will divide it by 3. I didn't use the log 10 thing here, so that may be a mistake or what. I mean, you can just kind of edit that later. It's fine. Okay, but I just use this as my threshold. Okay, technically I should just do a log 10 here as well. Okay, 10 times, yeah, maybe, yeah, later. Yeah, maybe, yeah, I'll just do it for consistency's sake, you know. So let me do 10 times log 10. Max of all this, divide by 3. And likewise for here, 10 times log 10. All of this, divide by 3. Maybe you don't want to divide by 3, maybe divide by 2 is better. Yeah. And this will be used as a threshold for the peak prominence, which I was talking about just now. Okay, so yeah, we found out that using a divide by 3, you will detect way too many peaks. So I didn't want that. Maybe I'll do a divide by 2. Yeah. Or maybe divide by 1.1. Give and take, you know, give and take. Yeah, maybe we'll do a divide by 2 and we'll see how things go. Now you'll see that I use a findpeaks input dB, which is the so-called y values, f, which is the x values, the horizontal axis. Then I use peak prominence and threshold input, which I actually defined over here. It's my input, which I call, I use the maximum peak height to sort of use as a reference point. Same thing for the outputs. Now, what is all these things over here? Okay, if you take a look at how the syntax is over here, basically, if you have two of these locations here, okay, you can output the first. There's the first what do you call that? Peaks. The first thing, the leftmost so-called data point, or the output will be called peaks. Okay, peaks is basically, it gives you the local maxima returned as a vector of signal values. What does this mean? Okay, if you take a look at here, for example, over here there's a peak at the value of maybe 1.17. Okay, 1.17 dB. Okay, so what if you want to know the height of all these peaks, then this PKS vectors will tell you what the heights of these peaks are. Okay, and more importantly, we also want to know where the locations of the peaks are. So this is this LOCS, locations vector. Okay, so locations vector will give you the so-called x coordinate of the peaks, which is here 2 times 10 to the minus 3. Okay, so the first one is where I put my the peak heights. The second one is where I put my peak locations. Now, what is this peak data dot thing over here? And what is this peak data thing dot? Okay, so this is something known as data structures. Okay, so let's say let me explain a little bit of data structure. So let's say I have two arrays. A equals to 1, 2, 3, right? And B equals to 4, 5, 6. All right. So these are two arrays of information. Okay, and basically, if I want to return all of this data to a function, I will need to if A and B are supposed to be returned through a function, I will need to, sort of have separate, A and B over here. I need to type in A and B. I assume you know how to do functions already. So, I don't want to do that. I just want to return one item, and that is something called peak data. Okay, so let's say I have data.a equals to A. And what happens? Okay, I have made a new variable, and so it's a package. It's sort of a structure. They call it a structure. So in this structure is basically a box. Okay, a box where you kind of put all your information in. It can be an array. It can be a string value. So let's put data.b equals to b and see what happens. Now this data structure will have two pieces of data. I can even put in data.f equals to f. So what's data.f? Okay, if I look at this data structure here, and then I take a look at this thing called field, and I look at this thing called f. So data.f over here will actually just be whatever I defined it to be, which is over here the so-called the string of values, okay, the values that I have. Why does it make it convenient? Because now instead of having to return multiple pieces of data through this function, I just need to return one thing, and in that one thing I will have my data structure with every single thing, okay, which is my input peaks in decibels, output input peak frequencies, output peak in decibels, output peak frequencies. So if I run the script and you look at this thing called peak data, I will have my input peaks decibels, which is 11.76, not 1.176. Now my input peak frequencies, which is over here. Again, output peak decibels, output peak frequencies, okay, all nicely contained in this. Okay, and Okay, and the other thing here I did was this. Okay, so this is the first part of my code. All right, this is the first part of my code. It basically gives you all this peak data. Okay, it gives you all this peak data, and it kind of okay, let me put frequency data, and it gives you all of this. It gives you this. It returns you all of these things here. You see, input peak dB, input peak frequency, output peak dB, output peak frequency. Okay, now thing is this, we have sort of found our peaks already. Okay, so how then, you know, we want to kind of automate our process, right? And wait, let's take a look at the graph before we go. Okay, so you see, if I do this over here, you will see that I will have several peaks now. In fact, a little too many, because all of this technically is noise. I don't want to deal with it. Okay, so I just want all of this here, all of this data here to be counted, whereas all this other noise data here, I don't want it to be counted. So I should reduce my threshold. This is really up to you to decide. So maybe instead of 2, I'll give it 1.5. Okay, 1.5. All right, it's really up to you. Okay, 1.5 still not a bit too much. Maybe I'll just give a 1.2, and maybe that's the last adjustment I'll make. Okay, so this is the peak finder. All right, I think this is about right. It will detect most of the peaks here, and all of the peaks here sort of get detected as well, but it's not really what I want. Okay. Okay, now thing is this, there are so many peaks. All right, there are so many peaks, but I only want to basically find the frequencies and the complex gain of the, all right, remember I have all of this frequency data, right? I'm only interested of finding my complex gain, or rather the input and output data at this particular input peak frequencies. Okay, so basically 2 times 10 to the minus 3 hertz is my thing. So that's the input peak. Okay, and not only I want to find my input peak, but also all the input peak magnitude and the output peak magnitude. Okay, the the Fourier transform of the input and the output at this particular frequency. Okay, so if you are familiar with Excel, this is somewhat like a VLOOKUP array thing, and we are trying to put it in MATLAB. Okay, we are basically trying to put this in MATLAB. Okay, so yeah, so this is what we are talking about here. Okay, so let's take a look at this next part. Okay, basically I need to find the indices. Okay, I want to find, okay, like I was saying before, I wanted to find this index here. So this is actually my 0.00 2 times 10 to the minus 3 hertz. This happens to be at row 21. Okay, row 21. And at row 21, I will have my corresponding input, which is the Fourier transform is minus 0.0471 minus around 15i. Then I also want to find row 21 at column 3, which is the Fourier transform of my output at 2 times 10 to the minus 3 hertz. So I need to find this index number 21. Okay, how do I find the index number 21? Okay, so the way to do it is basically, again, with the use of peak finder. Okay, with this peak finder, again, I put this input dB, and I use the input threshold again using the min peak prominence. However, this time I did not supply the vector which contains all the frequencies of the various peaks. Okay, again, I did not supply the frequency of this. I did not supply the frequency vectors. So remember, we have this y omega and omega. Normally you're supposed to supply both of them, but I don't supply this anymore. Okay, so what happens? So the peak finder will actually just plot this y omega against, okay, 1, 2, 3, 4, ... all the way through. Okay, so because now I don't have the frequencies, I will need to plot y omega against 1, 2, 3, 4, etc. So let me just demonstrate to you what that is like. So yeah, let me remove this f and we'll see what happens when you take a look at the figure. Oh, let me clear the figures first and let's try again. Okay, now you see, instead of plotting it against frequency, it's now plotted against the the index number values. So it goes from 0 all the way to 20,000 because we have 20,000 elements. So let's say over here, let's say this is the peak that I'm very interested in. What index number is this? This is the index number 21. So now this is a clever way of, or rather it's a practical way of finding the index number of the frequencies that we are interested in. Okay, so this is index number 21. And what's index number 21? Basically, if you take a look at the frequency data, remember index number 21 is where we have our 0.002 hertz, or 2 times 10 to the minus 3 hertz. So this is what peak finder can do. It can return you the input, the index number. So what I basically had to do is, okay, write in this syntax, okay, it will give you the peak values. Okay, it will give you the peak values. Okay, the peak values here, and also the input peak index. Okay, so before we actually had the height of the peaks as your first output, and then the frequency of the peaks as your second output. But now that we did not supply the frequency of the peaks over here, we are not going to supply the frequency of the peaks as outputs, but instead this will actually output the peak index number. So let's just demonstrate that. Okay, PKS, peaks and index number, equals to find peaks, all of this, and see what happens. Let's take a look at the index numbers. Okay, 21 is identified as a peak, 41, 61, all the way through. Of course, this is way too sensitive, alright? This is way too sensitive. So maybe instead of divide by 3, I'll just put I just want the maximum peak, right? Okay, so I just want the maximum peak. So let's find the, okay, so it's just hold on. Find peaks, yeah, times 0.9, clear, I just cleared all my variables. So funny. Okay, let me do this again. All right, so yeah, basically that loads back my values, okay. Yeah, so now let's again do this. PKS index number equals to peak finder, or find peaks. Okay, that's the correct one. Find peaks. What's your first thing? I need to put in the data, absolute of, for example, input. Okay, I didn't do the logarithmic thing this time, but you should put it in if you want to. Okay, I'll go for mean peak prominence, and that'll be, the tolerance will be absolute input, maybe divide by 10. Okay, Oh yes, absolute of the max of the absolute input divided by 10. Sorry. All right, so you can see now we have the height of the peaks here. There are only 2 peaks, and the index numbers are 21 and 19980. Okay, so this is actually functioning the way I want it to. Okay, and that's maybe, I think, why I didn't bother using the logarithmic thing as the threshold, because that actually helps to, you know, helps to identify the peaks. Okay, so I guess logarithmic using plotting your peaks in dB is good for visualizing, but for finding peaks maybe it's not as good an idea. I mean, give and take. Okay, so these are just some learning processes you go through, or I'm going through even now as I'm casting this screencasting. All right, so yeah, maybe this we should change, instead of using logarithmic, we should use just an absolute scale. Okay, so now that you have your index number, how are you going to you know, find your values at this index number? So for example, yeah, over here your input again, or rather your frequency data is here. Frequency data here. I look at index number 21, and I want my frequency, I want my input Fourier transform, and my output Fourier transform. How do we do that? We use this thing called element search. Okay, elements. Ouch. Sorry, I just banged my elbow. Element search, and this is basically your VLOOKUP function. Element search MATLAB, and this is very useful. And basically, it just says find array elements that meet a condition. Wow, I'm 30 minutes in. Okay, so I'll stop here. I will continue more in the next video how this thing actually works. Thanks for watching.